Hello everyone, welcome to Tech Talk session number 13. Again, I'm Paul Stechik with NEPSI. Thank you for coming. This week's session we're going to be talking about filter-ready capacitor banks and why renewable developers should specify them. In this presentation I go a little bit long, potentially 45 minutes, even an hour, and it's difficult to tell how long. So I got a question for the people who are attending. Would you prefer that these last only a half hour and I break them into two? Or do you prefer that they go for the full length? And even if you can't stay for the full length, you can always view them at a later date because everything is recorded. So that's kind of a question for the crowd that are showing up. What's the preference? So we're going to get on with the presentation right now. And so again, today's Tech Talk is filter-ready capacitor banks. Don't forget the PDH credits, and don't forget to ask questions as we proceed along in the presentation. So let's talk about some basics first. Renewable power plants. Most oftentimes they have some type of reactive power requirement. There's an interconnect agreement, and reactive power is required for the facility, either for power factor control, for steady state voltage control, dynamic voltage support, voltage stability. Some type of interconnect study is required. The interconnect study gets done and a determination is made that reactive power is required. Sometimes that reactive power can be quite significant. You can kind of see here 48 megavars for this system here. So 48 megavars in a metal enclosed system that we supplied quite a few years ago at this point. So it's very often that a capacitor bank is used as that source of reactive power. But sometimes a harmonic filter may be specified if there are harmonic related issues, and sometimes STATCOMs. STATCOMs can provide reactive power, but they are very expensive. But a STATCOM sometimes is also a requirement. Provides a different function than a capacitor bank because it's got dynamic VARs. It can respond dynamically and very quickly to reactive power requirements of a facility. And then sometimes the inverter can be designed to actually put out reactive power. And in that case, it's a potential that the capacitor banks would not be required. There obviously is cost associated with each of these solutions, and capacitor banks happens to be the least costly option. So it is oftentimes a preferred option because we're looking to reduce costs on the overall project. So that's a key driver to what gets chosen. When installing capacitor banks, there are some key issues, and one of those is resonance. You install a capacitor bank on the system, you have resonance. So just like on industrial systems in the renewables area, resonance is a key concern when installing metal enclosed capacitor banks or even open air capacitor banks. So if a resonance occurs at a dominant frequency, at a frequency output of the inverter, the solar inverter, or by the wind turbine, if there's a corresponding resonance at the frequency output, harmonic frequency output of one of those devices, then there's a good chance you got a problem. Resonance invariably will cause you to fail IEEE 519, and that's really the point that we're making down here. Oftentimes, harmonic studies and resonance studies are part of renewables project. I was on the phone the other day with somebody, and they were saying that about 50% of the projects will require a harmonic study of a sort. So oftentimes what we have found is that when those studies are conducted, the answer or the recommendation that comes out of that study is you might need a filter, you might not. Remember, harmonic filters are installed to prevent resonance in many cases, and also to provide harmonic filtering. So remember, filters provide, they prevent resonance, they provide reactive power, and their third function is to consume harmonic current from the wind turbine or the inverter if necessary. But oftentimes it's the prevention of resonance that you're after. So this is just a typical study that you might see, the recommendations that form part of that study. And this is actually just a copy of a report that I've seen, and it's very typical. You might get a statement that you might want to tune around resonance, or you might want to wait and see what happens after you install the capacitor bank. But this wait and see concept does not fit well with the developers because they're trying to turn over the plant. There is a schedule of activities. They want to buy the equipment, get it installed in a substation. So a wait and see does not work that well. And if after startup and commissioning, it is determined that there's a harmonic resonance issue or the IEEE 519 limits are exceeded, the corrective measures could take anywhere between, say, 10 and, say, 30 weeks of time, and that could prevent the turnover of the facility. So this solution is not the greatest, and it is one of the reasons why NEPSI always recommends filter-ready cap banks, and that's what we're going to be talking about today is filter-ready cap banks. So one of the first issues that we see is that harmonic analysis results are most often very inconclusive. They're not conclusive. And so we're going to go through each one of these points one by one, and I will briefly touch upon why these are contributing factors to a harmonic study being not conclusive. So resonance and near resonance causes harmonic current amplification. So in another presentation, we talk about harmonic amplification, and here when we have resonance, this plot shows that we have current amplification. So the blue curve here represents amplification. If I have a fifth harmonic right here, say right at the fifth, I'm going to see an amplification of maybe 2 or 3 times. So that would represent amplification of the current that is coming from the inverter, the solar inverter or the wind turbine. The peak of this amplification factor, if it lines up with a harmonic, can be quite significant. We're showing 80 times here in this case, 80 times. So that's quite a bit. The peak of that is based upon this equation and is based upon the X over R of the system. The one thing you learn when you do harmonic analysis is that knowing resistance of the network is very difficult. If you think about it, you look at the nameplate of a transformer, there is no X over R ratio given in that, so it's something you don't know. And how the resistance of the network varies with frequency is also unknown. You have proximity effects, you have skin effects, and the resistance of the network is not well known. So how much amplification you get will change, and the assumptions you make could possibly change your results. So it makes it difficult to actually understand what the implications of amplification are. Okay. The other thing that the resistance of the network does is it changes the width of the resonance. How much impact does this resonance have? How thin it is, or how fat that curve is. So if we were to kind of zoom in on this, you can see the area in red represents harmonic current amplification. So even if my resonance is off, in this case we're showing maybe a 5.5 harmonic resonance here. Even if the resonance is off, I'm still getting current amplification, sometimes 2, 3, 4, or 5 times the value that is actually being injected into the system. So current amplification is something to think about. When you look at current amplification, you can kind of see here, we just have a very simple collector system here shown. Maybe you have some wind turbines, you have some solar arrays, some solar inverters, the collector bus, a cap bank here, transformer, and the source. When you have current amplification, the harmonic output from the inverter here is amplified, and the harmonic current is amplified here and is increased through this area. The point of common coupling happens to be out here. So the point of common coupling falls into that area where the current is amplified. So even inverters that are putting out very, very low levels of harmonic current, we can still get current amplification out here, and we can exceed the IEEE 519 limits. Okay, on with, all right, so let me return back. So let's talk about IEEE 519 limits. The IEEE 519 limits are very restrictive. Here's my flashlight. So if I were to go look at the IEEE 519 limits, the first thing you note is that the standard requires that we are in this row here, and this is the most restrictive row. And again, these tables are split up based upon the voltage level of the PCC, or the point of common coupling, or the point of interconnect, the POI. So if the point of interconnect is at 69 kV through 161 kV, we're in this bucket here. And we're saying that the harmonics between the third and the 11th, basically anything greater than or equal to the third or less than the 11th, must be 2% or less. This even more restrictive when you look at the even harmonics. It's 25% of that, so just 0.5% for even harmonics. So that would be the second, the fourth, the sixth, and so on. So quite restrictive in that nature. We kind of flip over and we say we go to even higher point of interconnect voltage, one at 161 kV. You can see that the value drops to 1%. So a very restrictive requirement by IEEE 519. So any current amplification that you get of a very relatively low value can be amplified to a point where you exceed IEEE 519. So if your interconnect utility is one of those utilities that are hooking up a meter, and they're doing the metering after your plant is installed, after you install those capacitor banks, there is a possibility, if you're in that range where you might have resonance or you're near resonance, the amplification factor can easily cause you to exceed the IEEE 519 limits. So it's something to be of concern. For multi-stage capacitor banks, you can see that the resonance concerns will go up. We will, each and every time I add a capacitor bank to the system, we will get a different resonant point. So we add a 7 megavar bank, we have a resonance near the 11th. We increase that to 14 megavars, we will get another resonant point perhaps around the 8th. And then again, we can get one here at 6.5 and something at 5.5. So we have multiple resonant points that we need to be concerned about. So we have multiple concerns for current amplification, and this is a major concern for multi-stage cat banks. But many renewable plants are using multi-stage cat banks because they need to control reactive power based upon the power output of the wind farm or solar plant. So, and now we have this next concern is, how do we deal with multiple harmonic current sources? So when a studies engineer, when they do the harmonic study, what they do is they'll look at, they'll take all the wind turbines or all the solar inverters, they'll line them up onto the collector system, and they have to inject the harmonic current at each and every frequency. So there might be 100 inverters, and we'll put 100 inverters on the collector system. Each inverter will have a fifth harmonic current output with a phase angle. And the question becomes, how do you account for the summation of those harmonic currents? One way is just to directly add them. Okay, so if I were to kind of take a look at just a wind turbine, the harmonic output, you can see that here there are values of current distortion as a percent of their output, and there's similar things can be done for a solar inverter. So the question becomes, how do you add those? One way is to make an assumption, say they're 80% additive or 70% additive. So remember that if each inverter is putting out the harmonic current and there are slight phase angle differences, they do not directly add. They add at a percentage of that value. So there's an assumption that's made. And the most conservative assumption is that we just say they directly add. But a lot of times that will put you past the IEEE 519 limits. So then you can start looking at, well, let's come up with a way to reduce that value, assume 80% or 70%. IEC has a rule, or what's called their general summation law, that sometimes gets followed. And that's the formula over here. They're using this formula here, UH equals the summation of U to the alpha and raised to the alpha. So if I kind of flip to the next slide, you will see that there's that the formula is based upon values of alpha based upon harmonic value, okay, based on harmonic value. So when the value is 2, that's more or less the summation of the squares, okay, so basically like an RMS value. The 1.4 value will predict a harmonic addition to be slightly less than what the summation of the squares, square root, would provide. So this is a way to to drop down the harmonic current injection in a meaningful way and perhaps bring you within IEEE 519 limits for the study. But the question is, in reality, what happens? And this is a concern. You're doing a study to determine if your capacitor bank will be resonant, and the question becomes, is that still accurate, these assumptions that you make during the study stage? The next question is harmonic current injections from the wind turbine and inverter suppliers. Are they accurately provided? Are they accurate in what they provide you? And that's a concern that you should have. Those harmonic current injections are based upon tests that they do in a laboratory, and not necessarily based upon the tests at the wind farm where you're located. So this is a concern: is what is the real harmonic current injection? What will it look like on a system with the system source impedance profile that you're giving it? So something to think about. So the last bullet point here is that the source impedance changes, collector system capacitance variation, errors in modeling, nearby transmission level capacitor banks, line and collector system outages, and many other factors can contribute to errors in the harmonic study. Okay, so based upon the above, harmonic analysis results are never 100% conclusive. So a backup plan should always be implemented. And that's really the message of this section of the presentation: is you got to have a backup plan. The backup plan when capacitor banks are applied is a filter-ready capacitor bank, and that's what we recommend, a filter-ready capacitor bank. So, in concept, why is this important? Well, you're going out, you're purchasing either a metal enclosed harmonic filter system here, or you're purchasing an open rack harmonic filter system here. And this is a multi-stage capacitor bank. I said harmonic filter, I meant capacitor bank. You're buying a metal closed cap bank or an open air capacitor bank. You're creating an investment. You're installing it in a substation. You're going through a major effort. You have costs, engineering costs, installation costs, commissioning costs. In the end, when you do your startup, if you have a problem, you need to have a backup plan. Otherwise, there's a potential that you have to scrap everything you purchased. So planning for the possibility of a resonance issue or a harmonic distortion concern would be beneficial, and that's what we're talking about here. I'll make a point that NEPSI does not build open air harmonic filter systems, open air harmonic filter systems, or open air capacitor banks. We're only in the business of manufacturing medium voltage metal enclosed capacitor banks and harmonic filter banks. And they have some advantages when it comes to this filter-ready concept. So what's the filter-ready concept? Okay, so the filter-ready concept, the first thing is, if you've been around for the harmonic filter design presentation, the first thing you know is that the capacitors in a harmonic filter have a higher voltage rating. Okay, so you need to specify capacitors to have a higher voltage rating, and that's what we're showing here. At least specify HD, which is a heavy duty, or an EXT, extra heavy duty, which means that the capacitor is going to have a percent, depending upon which manufacturer you go to, a value of voltage rating higher than its nameplate rating. It's going to be able to handle a higher voltage rating. But then you perhaps want to add an additional, say, 1,000 volts rating. So you're dealing with a 34.5 kV collector system, line to neutral is 19.9. You would perhaps go with a 20.9 kV rated capacitor and then rated HD. And what that means is that I would be able to take that same capacitor bank and apply it as a harmonic filter. I can add reactors to that capacitor bank and convert that capacitor bank to a harmonic filter. That's the key concept here. If you had used just normal capacitors, standard duty capacitors, you would not be able to convert that capacitor bank to harmonic filter bank. And the reason being is that the iron core reactors or the air core reactors in an open air system that are used to tune that capacitor bank create a voltage rise on the capacitor bank based upon 1 over basically n squared of the tuning point. So a fifth tuned filter would approximately be about 4 to 5% voltage rise, which would mean that you're exceeding the capacitor voltage rating. The filter ready concept should include connection points. For cabling. If we have a capacitor bank and we need to add reactors to it, we need to have connection points. So we should account for that in our filter ready capacitor bank. We as metal closed system will put what we call pass-through panels. We'll get the system ready to incorporate a harmonic filter reactor, and I'm going to talk about this all more in a minute. Your substation design should accommodate the increased space requirements for harmonic filter. So do the drawings up front. If you're doing a filter ready cap bank, if you want to be ready for it, then you should plan for it up front. Increase the pad size, increase the size of the substation to accommodate that harmonic filter should that capacitor bank have to be converted. The upfront cost for a filter ready capacitor bank is minimal, and the cost advantages to dealing with the harmonic resonance problem or harmonic distortion problem are significant if you are ready for it if the time comes. So site provisions are necessary, and this is really dedicated to a metal closed system, but it somewhat will also include what you would need to do with an open air system. Concrete pad or space. You need space in the substation. You need to increase the concrete pad. We're going to talk about what that is. You're going to want to install metering at your site. And the reason you want to install metering is that it should be like a Schweitzer 735 power quality meter, an advanced power quality meter, something that can measure harmonics, something that can log harmonics. Install that in the capacitor bank feeder cable somewhere in the feeder breaker area, and also install that on the main breaker of the plant, the main secondary breaker, and the main primary breaker, so both sides of the transformer. And in this way, if you have a harmonics problem, you have the ability to do the design of the harmonic filter quickly. You don't need to send somebody out to take measurements. You're just going to call this device up over the network, over the internet, and download the data, and that will be enough data for a harmonic filter design guy to say this is the filter design that you need. So installing that metering is very important. It's a way to answer and address a harmonics issue very quickly. At the time of conversion, you will need to purchase a reactor and potentially an aux capacitor, which would be associated with a C-high pass type filter, and then potentially also resistors, resistor section. So you're going to be adding this to that capacitor bank to create a harmonic filter. We're going to be installing rear pass-through at the rear of the enclosure. We're going to have to install this stuff, the reactor enclosure, the aux cap enclosure, to convert that cap bank to a filter, and then you're going to have to recommission it. So I think the next couple of slides kind of show it, what we do. So the yellow area represents the filter ready components. The components that are added to a capacitor bank to create a harmonic filter. So you're buying a capacitor bank here, down here. You have the fuses for the capacitors, and you get the terminals connected to some type of switching device. The area in yellow is what you can add on later to convert a capacitor bank to a harmonic filter. The key here is the capacitors must carry the proper voltage rating. So this kind of shows how it looks in a three-line diagram. You can see here that the shaded yellow area is what we can add at a later date. Okay, nothing else changes. So it's quite simple. We just need to have terminals. For the metal closed solution, we're going to put rear panels on it, or side panels. These are pass-through bushing panels. Basically, we're looking to go from the capacitor bank to the reactor bank, okay, and then back into the capacitor bank, because our cables are now in the capacitor bank. So this is what's required. From a space standpoint, what the reactor enclosure looks like, what the resistor enclosure looks like, in that aux capacitor, those components, aux capacitor, resistor, and reactor, will go into this area here in yellow on the right. So it's here on the right, this whole area. So basically we're doubling the depth doubling the depth of the metal enclosed cap bank. And then a floor plan like this. So from a designing standpoint, you're designing a substation. All that we're asking you to do is to take the floor plan that we have and double the depth. Basically double the depth in your substation. So not a big deal. You do not necessarily need to have the concrete pad poured at the time of installation of the metal enclosed capacitor bank, but you do need to make sure that you allotted the space for this enclosure. The three types of filters that can be used to accommodate filter that can be utilized in a filter-ready cap bank is the standard notch filter here, the high pass filter here, which is just basically we're adding a resistor and a reactor, and then we got this C high pass filter, which is resistor, reactor, aux capacitor. Okay, so there is an increase in cost and complexity as you go from notch filter towards the C high pass filter. Notch filter, this is just a quick impedance profile. We have other presentations that will be addressing the characteristics of notch filters, high pass filters, and C high pass filters. So we won't go into too much detail here. The high pass filter, we can change the characteristic of the filter by changing the value of resistance here. And basically you can see that the characteristic of the filter can change. Basically as we bring the value of resistance down, we can change the high frequency response of the filter, and we can also change the characteristics of the filter at the tuning point. You can see here the most bottom curve section of the curve here, right where it almost touches the fifth harmonic, that resembles a notch filter. That would resemble basically an impedance here of that resistor that is very high. We take that resistor, we bring it to infinity or to a very high value. What do we have? We have a notch filter. So adding a resistor to a notch filter creates a high pass filter that gives you control over the characteristics of the harmonic filter. So this is a C high pass filter. The characteristics of a C high pass filter are identical to those of a high pass filter. The key difference here is we've added a aux capacitor. And the purpose of the aux capacitor is to tune this reactor to the fundamental. And we're doing that because we're trying to reduce the losses here. We can take away the fundamental losses at this location. That's really the purpose of that. And by doing that, what we can do is we can drop the value of R to a very low value. I will call it a super damped high pass filter, and we can have a greater impact across the whole entire frequency spectrum. So it's a very common type of filter system to use. Filter-ready concept, open air configuration versus metal enclosed configuration. We'll zip through some slides here just to show you how the open air configuration compares to the metal enclosed configuration when you're thinking about the filter-ready concept. To the right here, this represents the capacitor bank. And what we have here is a shunt reactor bank, and we have two shunt power capacitor banks. So it's two steps of 12.5 megavars for capacitors, one step of 12 megavars shunt inductors. Okay, so NEPSI has a product called a hybrid shunt capacitor, shunt reactor bank. And remember that oftentimes renewables, they have to install shunt reactor banks for light load conditions to consume VARs to possibly bring down the voltage within the collector system during light power output conditions. So we detail out everything that's necessary to install this system. There are some advantages with the metal enclosed solution. The key advantage is that we can change the switching device in here from a common Southern States cap switcher to also include other switches such as an ABB VD4 or VD4CS or an HD4. There are some advantages to doing that, and the key advantage is the elimination of the feeder breaker to the capacitor bank down here. Something you can't do with an open air solution, something you can do with the metal enclosed solution. So if you look at the footprint area of this is a filter ready capacitor bank in the open air configuration, and what you see here is a switching device in the middle here a bus bar stand. This area here represents the magnetic clearance requirements for an air core reactor. And then, of course, we have the capacitor bank up here on the top. It's an open rack capacitor bank. So we have two stages, 1, 2, and then we have the shunt reactor bank here. Okay, so in all, there's an area requirement for this of 7,600 square feet, and that's a pretty significant area. So we can do the same design as metal closed, and this is a 3-line diagram. And in this case, we're using breakers instead of cap switchers, and we're using a breaker over here instead of a reactor switching device. So we have a shunt reactor, RC snubber network for switching purposes, and then 2 stages of capacitor banks. Take the same system, and you can see we've shrinked down the area. In fact, our area requirement now is only 765 square feet, so we're only 10% of the open air solution. Quite small, and it's filter ready, and it's quite easy to change. So just kind of zooming in on it, you can see here we have this add-on enclosure section. You may or may not need it, but you're prepared for it should you have a harmonics problem. We got the shunt reactor on the end. It's an iron core shunt reactor. Okay, so it's insulated in oil, and it's iron core. So all in all, a very small footprint. Here's a side view of the arrangement. And substation. And the difference between these slides is there are occasions where a air core reactor for the shunt reactor portion, it makes more sense as air core rather than as iron core. There is at about say 6 or 7 megavars, there's a crossover point where air core reactors become less expensive than iron core, so you may have a desire to put air core reactors in there. The key here though is look at the size of these shunt reactors. They're huge. They're almost as big as the whole capacitor bank. So, and you get the magnetic field clearance requirements around those that you must abide by. So here's an example of how that might look. And this is a project that we did a while back called Bobcat Bluff Wind Farm. In this case, we had 2 stages of 15.7 megavars and a 4.1 megavar shunt reactor bank. So you have the shunt reactor bank here on the end, plus your 2 stages of capacitor banks. The other thing to note is we have some outrush reactors up here. We're limiting outrush reactors here to protect breakers in the substation, the breakers over here. So that will be a tech talk for the future, for a future session, is how to size those outrush reactors and why they need to be installed or why they might not need to be installed. So I kind of got a common theme here, rules of thumb, the do's and don'ts. So the do's is specify filter-ready capacitor banks, specify harmonic rated capacitors considered an HD design, harmonic rated or heavy-duty design, add an additional 1,000 volts to that design. Remember that the kvar output of the capacitor bank will drop by the voltage squared. So if you're adding 1,000 volts to the capacitor, you will need to buy more megavars because you've added 1,000 volts, and the difference is basically by the voltage squared. So say it was a 20 kV capacitor, you go to 21, you would need to buy 21 squared over 20 squared times your megavars to get that same megavar output. So think about that additional megavars, and really that's your cost difference, is that difference. And it's really pennies on the dollar at this point. Specify that the provisions in the capacitor bank to allow for easy conversion to a harmonic filter bank. There are some design things that NEPSI does to make sure that if you convert a capacitor bank to a harmonic filter bank, that is easy. Bus work inside needs to be spaced out enough to accommodate incoming and outgoing conductors. There must be removable back panels to allow for the insertion of bushings or some other type of way to get the cables from the capacitor compartment to the reactor compartment. Specify metering. Consider that Schweitzer 735 advanced power quality meter or an equivalent type power quality meter that can do data logging, that can measure harmonics, that allows you to dial in across the network, across the internet, to get the data necessary to design filters. And then plan ahead. Put the converted filter-ready capacitor bank into the substation layout drawings. Do this up front. If you understand what's ahead of you, if at time of turnover or if at time of startup and commissioning, you determine that you have a resonance problem, while knowing that you have the substation space and that you already have a preliminary pricing on the conversion costs, it will make the process very quickly. We could potentially convert a capacitor bank, a filter-ready capacitor bank, to a harmonic filter bank in as little as 10 weeks if you had planned up front. Do not use standard capacitors in your renewable plant, because it does not allow for conversion of the capacitor bank to harmonic filter bank. So always go with heavy duty, and I would recommend plus 1,000 volts at least, so you can accommodate the harmonic currents. And don't assume that the study, that if the study says that you will not have a problem, that you will not have a problem. There are, and we've covered it in this presentation, there are many places where a harmonic study can go wrong. Okay, the input data and all the other assumptions that go into it. It's a great first look at the possibility of a problem. But even if the study says you do not have a problem, always assume that you might have a problem. And then you might also want to consider going with what I would call a lighter version of a harmonic study, and putting the cost savings into your capacitor bank, converting that capacitor bank from a standard capacitor bank to a filter-ready capacitor bank, and pulling a little bit of cost from the harmonic study, because there's not a whole lot of cost there. So again, go to our webpage. We have lots of information on our webpage. And if you missed our other Tech Talk videos, there's a playlist on our YouTube channel. So this is number 13. So we have a lot of good videos that have been produced. Next week, well, not next week yet. So conclusions: harmonic studies are prone to error, right? Key conclusion of this presentation: specify filter ready configuration. It will potentially save you in the end. And the metal enclosed configuration is more suitable for filter-ready capacitor banks when you compare it to an open-air solution. Better lead time, and really the lead time is better because we can use iron core reactors, which have a lead time of about 8 weeks, versus air core, which is typically in a 20 to 30 week lead time. We have a smaller footprint, so it's easier to install that filter-ready cat bank into your substation. Next week, I asked a question. I don't know if we took a vote on it or not, if people have answered it, but at this point in time, our plan is to talk about automatic power factor control. How is it typically done at the medium voltage level? How do we set up our control schemes? What do we do in a main-tie-main situation? CT arrangements. We're going to talk about master-slave arrangements, steps versus stages, what we call sequence switching, and a bunch of other concepts. So we're going to move on to questions at this point. Don't forget to send us the code for the PDH credits. So. Okay, guys, I've had a chance to review the questions. We only have one question. I did take note that people prefer the full-length presentations. I think it's great. It's what I also prefer. Because if you have meetings, you can always come back and watch them. They're always recorded. Power factor control by far is preferred for next week. So we're going to be talking about power factor control and how we do it next week. Kyle had asked the question, what is generally the best filter type to gain compliance on high order harmonics? 17, 19, 21 emissions without amplifying lower order harmonics. Well, for sure, it's a C high pass filter or a high pass filter. Remember, high pass filters are generally used at frequencies above the fifth, and so C high pass filters for frequencies. Well, let's make sure I get it right because I might misspoke. High pass filters for tuning frequencies above the fifth. C high pass filters for the fifth and below. And the C high pass filter, you're looking to eliminate. The fundamental losses. So to go after the 17th, 19th, and 21 is a very tricky harmonic to go after, because when you put in a filter tuned to the 17th, 19th, and 21, or in that area, so say it was 17th, 19th, to 21th, I might tune my filter to 19, and I would use a high pass filter that was damped. And what that means is I've taken away the sharpness of the filter, and so it's not going to go down to near 0 ohms at its tuning point, but it's going to come down shallow. So I can pick up the 17th, 19th, and 21st harmonics pretty well with a high pass filter. You do have the resonance that sits on the lower frequency side of the filter that you need to account for. A notch filter by far will not allow for that. And if I could go back to my presentation, can I, or is that true? We could do it? Let's see if I can do this. All right, guys, this is something new, treading on new water, but there is a slide here, and I think it's worth showing to answer the question more in full. So here we go. So on this case, we just have two systems. The one on the left is notch filters. The one on the right is high pass filters. And we're just going to do a comparison of the impedance scans. You can see that high pass filters eliminate the resonance here. We eliminate the resonance concern. So the red represents the high pass filters. The blue represents notch filters. These resonances are a concern when installing notch filters. In almost all cases, when you install notch filters on a system, you have to go with a fifth filter first, then a seventh filter, then an 11th filter. When you go with high pass filters and they're highly damped, there is the possibility that you can tune the high pass filter up towards the 17th, 19th, or 21st. Still tricky, so it's something that you want to do simulation on, and it will definitely have to be a highly damped filter. So let me see if there's any more questions. What would be the recommendations on voltage source harmonics when we don't have voltage harmonic data from the utility at the POI? So that's a good question, and I recently saw a study where somebody was doing 1%. So they would put 1%. Putting a voltage source in your system. So somebody's gone out into the network. They've done some network measurements at the point of interconnect, that high voltage transmission bus. They've taken some harmonic measurements, and they measure a distortion. If you got that value, even putting that value into the study is very tricky, because you don't know the impedance behind that voltage. Just to put a voltage there with no impedance is not a great modeling technique. It's going to be a very conservative result. In fact, it's going to be able to drive a lot of current. So modeling voltage sources within your harmonic study is very tricky. If you don't have a value, then consider maybe 1% maximum 1%. Transmission level distortion tends to be lower than that, even lower than that, so maybe 0.5%. It's a tricky question. And what you know is also very tricky, and how you do that modeling is tricky. So it could easily force you into a harmonic filter by modeling that primary side voltage source. I think that's it for questions. I We'll wait one more minute, see if anybody has questions from my responses. If not, we will see you next week. I appreciate you guys coming on. All right, no questions. So you guys have a good week. We'll see you next week. Thank you for coming.